All right, today we're going to dive into a really fundamental question in electromagnetism, one that has some huge practical implications. What actually happens when you stick an insulator, what we call a dielectric, inside of a capacitor? It's a concept that is absolutely central to how we design circuits and store energy today. So let's start with a really practical problem. How do you make a capacitor more powerful? How do you get it to store more charge for a given voltage? Well, the secret sauce, it turns out, is the material you put between its plates. And to really get why, we need to connect the big macroscopic effects we can measure in the lab to the tiny microscopic behavior of molecules. So here's our roadmap. We're going to start with a key experiment, and that's going to give us some clues about the electric field. Then we'll zoom all the way down to the molecular level to really solve the mystery. After that, we'll look at some real-world consequences and finish up by tackling two classic scenarios you'll definitely see in E&M. Okay, let's get right into it. This whole story kicks off with a simple but honestly pretty profound experiment that shows you the hidden power of these dielectric materials. So, imagine this setup. We take a standard parallel plate capacitor, hook it up to a battery, and charge it up to some voltage. Let's call it V0. This puts a charge Q0 on the plates. Now here's the crucial part. We disconnect the battery. The capacitor is now totally isolated, which means that charge, Q0, is stuck. It has nowhere to go. Then, we take a slab of something like glass or Teflon and slide it right into the gap, completely filling it. The million-dollar question is, what happens to the voltage? And boom, look at that. The result is crystal clear. The voltmeter shows that the potential difference takes a nosedive. The voltage just drops pretty significantly. And remember, since that charge Q0 is constant, this drop in voltage is our first major clue. This whole phenomenon is what we call the dielectric effect. Now, to put a number on this effect, we use something called the dielectric constant, which we write as the Greek letter kappa. Think of it as a score for how good a material is at doing this. It's a dimensionless number that tells you how much that material can reduce the electric field and, as a result, the voltage. A perfect vacuum has a kappa of exactly 1. That's our baseline. Every other insulator you can think of has a kappa greater than 1. So, the whole macroscopic effect boils down to these two beautifully simple equations. The new voltage, V, is just the original voltage, V0, divided by kappa. And since we know that capacitance, C, is just charge over voltage, right? C equals Q over V, well, if Q is constant and V goes down, capacitance has to go up. Specifically, the new capacitance is kappa times the old one. Just like that, we've made our capacitor more powerful. But why? Why did the voltage drop in the first place? To figure out that why, we've got to look deeper at the electric field itself. This big macroscopic change that we just measured actually comes from something happening on a much smaller scale, all about how the dielectric interacts with the field lines between those plates. Just look at this comparison. On the left, you've got your standard empty capacitor with a strong, uniform electric field, which we'll call E0. But check out what happens on the right when we slide the dielectric in. The density of the field lines is way lower. The field is just weaker. And because voltage is basically the electric field times the distance, a weaker field directly translates to a lower voltage. It's as simple as that. So why does the field get weaker? Well, it's all about the principle of superposition. It's like a game of tug of war between two different electric fields. You have the original field, E0, that's created by the charges on the metal plates. But now, the dielectric material itself is creating its own field, which we'll call E sub I. And here's the kicker. It points in the exact opposite direction. So when you add them together as vectors, the net field that you're left with is weaker. And this brings us to a really critical distinction. We've got two different types of charge to think about now. First, there's the free charge. That's the Q0 we put on the capacitor plates in the first place. It's called free because it can move around on the conductor. But then you have this new thing, the induced charge, or Q sub I. This charge isn't free to move around. It's the charge that kind of pops into existence on the surface of the insulator itself. And this is the charge that's creating that opposing electric field. Okay, so we're getting so close. We know there's an opposing field, and we know it comes from these induced charges. But where do the induced charges come from? To answer that, we have to zoom way, way in and see what's happening to the individual molecules of the dielectric. First up, let's think about materials made of polar molecules. Water is a perfect example. These molecules are like tiny little magnets. They have a permanent positive end and a negative end, what we call a dipole moment. Normally, without any field, they're all just jumbled up, pointing in random directions. But the second you put them in the capacitor's electric field, E0, they all feel a torque and snap. They align with the field, like a bunch of tiny compass needles. Now, what about nonpolar molecules, the ones that don't have a built-in dipole? Well, something just as cool happens. The external electric field is strong enough to actually distort the molecules. It yanks on the negative electron cloud and pushes on the positive nucleus, stretching the molecule out. This creates a temporary induced dipole moment that, of course, also aligns perfectly with the field. And here's the beautiful part. It doesn't matter if the molecules are polar or nonpolar, the end result is identical. Deep inside the material, all the positive and negative ends of these little aligned dipoles are right next to each other, so their effects cancel out. It's a wash. But right at the surfaces, that cancellation isn't perfect. You end up with a thin layer of net negative charge on the side facing the positive plate, and a thin layer of net positive charge on the side facing the negative plate. And that is our induced surface charge. That is what creates the opposing field E sub I. Mystery solved. Okay, so now we know the mechanism. We've cracked the case. So let's talk about the consequences. How does all this affect the energy stored in the capacitor? And are there any limits? Can we just keep pushing this effect forever? Let's go back to our first experiment, the one with the battery disconnected. Here's something a little wild. The potential energy stored in the capacitor actually decreases. It gets divided by kappa. So where did that energy go? It wasn't destroyed. It was used to do work. The capacitor's electric field actually pulls the dielectric slab into the gap, and it uses energy to twist all those little molecular dipoles into alignment. The system's own stored energy is what pays for that work. But there is a limit. You can't just crank up the external electric field forever. If you make it strong enough, you can actually rip the electrons right off the molecules of the insulator. The moment that happens, your perfect insulator is no longer an insulator, it becomes a conductor. You get a spark, a catastrophic failure. We call this dielectric breakdown. Every material has a breaking point, a maximum electric field it can handle, and that's its dielectric strength. And these properties vary all over the place. I mean, look at this table. Air is barely better than a vacuum with a kappa of about 1.006, and it breaks down at around 3 million volts per meter. But then you have something like Teflon. Its kappa is over 2, and its dielectric strength is 20 times greater than air's. And then you get to these advanced ceramics like gallium titaniate, with kappa values in the thousands or even tens of thousands. This is how we can build incredibly small capacitors that store a ton of energy. Okay, to wrap things up, let's hit a classic problem that often trips people up. So far, we've only talked about the case where we disconnect the battery before inserting the dielectric. What happens if we leave the battery connected the whole time? Let's look at them side by side. On the left, battery disconnected. The key is that the charge, Q, is constant. It can't go anywhere. So capacitance goes up, but voltage and stored energy both go down. Now on the right, battery connected. The battery's job is to maintain a constant voltage, V. So when we insert the dielectric, the capacitance still goes up by that factor of kappa. But to keep the voltage the same, the battery has to pump more charge onto the plates. And because the battery is doing work to move that extra charge, the total stored energy in the capacitor actually increases. It's a subtle but absolutely critical difference. So why does any of this matter in the real world? Well, have you ever used a stud finder? That little device is basically just a capacitor. As you slide it along the wall, the drywall is the dielectric, and the capacitance is steady. But as soon as it passes over a wooden stud, you've changed the material between the plates. Wood has a different kappa than drywall, so the capacitance of the stud finder changes. A little circuit inside detects that change and bang, the light comes on. It's a direct application of everything we've just discussed. And that brings us right back to our original question. How do you make a capacitor more powerful? The simple answer is to find a material with a really, really high dielectric constant. We know there are materials out there with kappa values in the hundreds of thousands. So what's stopping us from making tiny capacitors that can store almost limitless energy? Well, the ultimate limit is a tricky balancing act. It's not just about a high kappa. It's about the fundamental trade-off between that high dielectric constant and the material's dielectric strength. And solving that particular puzzle, well, that's one of the holy grails of modern materials science.